So I want to introduce you, for those who are not familiar with Chandan Reddy. He is an associate professor. Words are too small on my screen. He is an associate professor at Wayne State University in the Department of Computer Science. He received his PhD from Cornell and his master's degree from Michigan State. He is director of the Data Mining and Knowledge Discovery Laboratory. His primary research interests are in data mining and machine learning with applications in healthcare analytics, bioinformatics, and social network analysis. He has published over 45 peer-reviewed articles, and his work is funded by the NSF, NIH, Department of Transportation, and Susan G. Komen for the Cure Foundation. So please help me welcome Dr. Reddy.
First, I would like to thank Kayu and Brandes for giving me this opportunity to, can everyone hear me? To come here and present about the big data analytics using Amazon to cloud platform, right? So I am Chandan Reddy. I am an associate professor working in the area of data mining, big data with applications to healthcare and social networks. So in the next 1.5 hours, we will talk about more about big data analytics, the algorithms for big data, the platforms for big data. How do we compare platforms? If you have a big data problem, what are the choices you need to make when you decide on the platform that to be used? And finally, we will talk about applying these algorithms in the big data platforms on the cloud computing environment. So how many of you have already downloaded the codes that were provided 1 week back, and we were able to run the codes? Okay. So the instructions, for those of you who did that's great. But if you haven't done that, that's fine. Okay. What I'm going to teach now, this will be more of a presentation than an in-lab session where I think you're all graduate students. You know how to run a command or do so. If you follow the instructions, they are pretty straightforward. What I'm going to teach are the concepts behind these algorithms, the codes that you are running. What are the algorithms associated, or how these algorithms are being scaled up on big data platforms? So what are these platforms? All these things related to big data is what you are going to learn in this tutorial. So firstly, I want everyone to go to this tutorial website, which is available over here, and it was also sent in the link in the emails. And all the presentation materials, codes, instructions, documentation, everything will be available on that website. Okay, so if you have laptops and you are planning to go to that website, I think that will be very useful. Okay, everyone, yes.
Can we share this or not?
Which one?
Can we share it with some other colleagues or not?
Yes, sure, yeah. Okay, so now let's go to the fundamentals of big data. Right? So what is big data? There are plenty of definitions out there. One of the simplest yet informative definition is the fact that whatever data, the complexities or the challenges, the voluminous, all these challenges for which the existing data processing technology is not sufficient, that data is termed as big data. Right? Often big data is all confused because of the word big. They think that big is always about voluminous data. But you can see there are more complexities in data than the volume itself. It's not just the scalability issue. There are many other challenges. And we will talk about some of these challenges as well. Heterogeneity in the data, noisy data, streaming data, longitudinal voluminous is one part of the complexity, but it's not the one and only complexity. Right? So the idea of big data analytics on big data is to find something that existing technology cannot find, or to make it more applicable in either real-time or voluminous data or any other complex scenarios that existing solutions do not provide accurate solutions. Right? Often the challenges will be capturing data, storage of data, searching in big data, sharing and analysis of big data. Right. So my expertise is in the analysis area, and so our talk is going to be mostly focused on the analytical algorithms. But before we apply any analytical algorithms, what are the platforms suitable for big data? We will be talking about those things. And some of you, whenever you see big data, this picture should have been, you should have seen this picture before. Volume, so the four V's of big data. So the volume, velocity, variety, and veracity. So veracity is in terms of the truthfulness of the data, the uncertainty in the data. So why is this becoming a huge problem? Is because of the development of several things. Everybody wants to digitize. The sensing technologies have become more accessible. Mobile phones are able to capture lots of data. And storage technology has improved a lot compared to 10 years back. Now, what used to be 20 years back a huge machine is now just a small, tiny device in a USB. You are able to capture even terabyte of data. Right? So the data, and nobody wants to throw away the data. They want to store the data in the hope that they will have available technology in the future to process that data efficiently. But that technology is yet to come. I mean, is in the process of coming, and so that's becoming a very important area of research. At this generation, once you are starting research, this is a very fascinating area to get into for you younger generation because of the vast amount of open problems that are available in this area. So. Why do you care? Is because the job market is out there. I mean, people are looking for people who have expertise in big data. 9 out of the 10 companies who are doing data analysis want to know if you are aware of data analysis, if you are aware of Hadoop, or if you are aware of some other big data technologies, and so on and so forth. So there is an interesting report from McKinsey and Co. that US could face shortage by 2018 in 140,000 people to 190,000 people who lack deep analytical talent, and around 1.5 million people who has the data analysis capabilities. And so desperately there are companies, there's government, everybody is investing a lot in this so that the next generation people, the computer scientists is now almost being replaced by the fact that they want data scientists, not just computer scientists to do this work. No offense to other fields, but data is becoming so important that this is encompassing all other fields within computer science as well. So that, of course, the world is getting digital. So big data is only going to get bigger. It's not going to vanish. And the term might be a buzzword, but I mean, it's here for to stay. Okay. So this is an era of big data. So the first important thing that you should think about when you talk about big data, before you talk about analytics, is what is the right platform. So how do I decide on the platform that is suitable? So for that, we did a survey. I'm going to talk about the survey for 15 minutes or so about what is a big data platform, because there was we studied a lot in the literature. It's not available about what to look for in a platform. Right? So I'm going to present the details of what to look for in a platform. For example, if you have voluminous and complex data, what will be the ideal platform for me? Right? What should I look into before I start the analysis task? So that's what you are going to learn in this tutorial about the various platforms, especially if you have real-time applications. So we definitely need to solve all these big data problems. We need platforms that are suitable, but there is no single platform that solves all the complexities involved in big data. If it is scalable, if it is real-time, if it's fault-tolerant, there are several issues surrounding so some of the problems that you are going to encounter will have some of these issues. If these are your issues and this is your objective, what is the most appropriate platform that you want to start your analytics on? So that is what we will try to address in this tutorial, the first half of the tutorial at least. And then we will talk about, on these various platforms that are available, what are the basic analytical algorithms that can be used to scale it up on these platforms. Right? So that will be the second part of the tutorial. In that part, in the later half of the second part, that's where the Amazon Cloud Computing will come. But before you get to that, first you need to know what are the platforms, more understanding of these platforms. And then you talk about what are the analytical algorithms. If I have these analytical algorithms, the most popular ones or the most important ones, right? So how do they scale up on these platforms? So those are the things that I'm going to talk about right now. Okay. So there has been a lot of research, and I'm going to give you the state-of-the-art work on all these methods. So when we decide on which platform to choose, there are several critical components that one has to understand, right? So one has to. So we can broadly classify them into first either a application or algorithm. We call them together because algorithm is the application is the drivers for the developing an algorithm. That's how we see it. And then there is this system or platform level requirements. So in terms of the actual data itself, storage or the how the data wants to be handled, there are some of the requirements. So, for example, from the application standpoint, you see how quickly do we need to get the results, and how big the data that is there to process. Right? From the application point of view, the algorithm that you are choosing, does it have several iterations? Because some will be very fast, but if it's only for one iteration. If it has to have multiple iterations, like the K-means algorithm I'm going to talk about, if it's multiple iterations, for example, a map-reduced Hadoop is what I'm talking about for those of you who know. Every iteration, it starts writing to the disk, and every next iteration, it starts reading to the disk. So for iterative algorithms, that platform is not a very suitable algorithm. We will talk more about it, what I just mentioned, but that is just to give you an example of, for iterative algorithms, there are only certain platforms that are the most suitable. Right? So that's the point. So in terms of the systems, will we have to, are we satisfied with the existing setup, or will we have to add more machines? Yes.
Just a minute ago, you were talking about dupe and MapReduce and how
yes.
on every iteration you write and access
yeah,
to this.
Yeah.
So are you saying that were you saying that you don't want to do that because it's so time consuming, or there are better platforms?
If you cannot go away from the model, that the model has to be iterative, there are ways to avoid using Hadoop and do something else. So that, because this becomes very slow when you have iterative algorithms.
Okay, thank you.
Right, so that's what I want to mention. By the way, feel free to stop me anytime. I mean, let's make it as like I should have told you. Thanks for asking, but I should have told you in the beginning. And I'm just going to have the slides and content. If you don't understand, just feel free to stop me. Okay, there's nothing wrong in stopping me at any time. So is the data transfer critical, or the hardware failures? Fault tolerance is one of the things. Okay, if you can code your own fault tolerance mechanism, fault tolerance mechanism is if your part of your system fails, is the algorithm still robust, right? So or does the entire setup is it going to it's going to stop working and so. So those are some of the issues. We will get back to these issues in terms of the characteristics of the platform. So we basically characterize these are the main issues that one can think of when we have a big data platform. So we started doing more formal characterization of all these issues. In the final chart I'm going to present in the first part of this tutorial. So and before we get there, we need to know what is out there. What are the platforms before we start thinking about these issues, what are the choices, right? So what is available out there is important for us to understand. Right? So the tutorial is going to be in the outline is going to be will look like this. First, we'll talk about the scaling factors. So what are the in the broad characterization of these platforms? What are the two categories one can think of? What are the kinds of scaling that are available? Scaling is basically trying to make the existing system better, improving the capacity of the system. So in terms of the scaling, there are these two terms: horizontal scaling or vertical scaling. And so the platforms such as peer-to-peer networks or the Hadoop and Spark fall into the horizontal scaling category. We will give at least 1 or 2 slides about each of these platforms, what it is, what is hot, what is not, and what are the issues with horizontal scaling, what are the issues with vertical scaling. And in the vertical scaling, supercompute is one very good example of vertical scaling. High performance computing clusters, multi-core, GPU, gaining a lot of popularity these days, and FPGA, which is kind of, even now people are using for very specialized applications. So we will talk a little bit about each of these platforms, and primarily any platform that you can think of can be categorized into one of these seven platforms in the product aspect, right? And then we will compare with these questions that we addressed, we were raising in the previous slide. What are the application level and the system level questions? we want to compare these platforms. Some of them are good in some aspects, some of them are not that good in some of the aspects. Right? So we will see for each of these 7 platforms, which of the characteristics makes it most suitable, and which of them is not suitable for that platform. Right? For example, if you have a real-time application, you need results in real-time fashion, GPUs are one of the best things that you do. Right? So if you have scalability, so you have several issues in big data problems. So that's what we will be discussing briefly in the next few slides. Right? So finally, as I said, let's talk about some of the analytical algorithms. Once you have a comprehensive understanding of comparing different platforms, I think at that point we can get into some of the popular algorithms, like we chose K-means and KNN because of their suitability to big data and the simplicity in the algorithm. Anybody can understand it very quickly. So I can talk about it very quickly. How these algorithms, which are such basic, can be scaled up to trillion data points, right? So billions and trillions of data points. If you want to scale up K-means algorithm, how many of you know K-means algorithm and KNN algorithm? So some of you don't, but I think most of the majority of you. Did you know about the K-means, how it's going to scale up to trillion data points, right? Billion. So this is what we are going to do. If you want to do clustering on big data, how the K-means algorithm, which is a very basic, simple, yet very powerful algorithm, how it's going to be scaled up to a very large data set. So that's what we are going to talk about in the last part of the program. And at that point, I can demonstrate that on Amazon EC2, and we can show I can show some of the basic commands and results. Any questions so far? So at least you get an idea of what you are going to play in the next 1 hour. Okay. So as I mentioned, scaling is the ability of the system to adapt to increasing demands in terms of processing, which is becoming very prevalent now, which was not one of the main issues, but now more than data analysis, how you scale up is becoming more important. So in terms of scaling up, there are 2 ways, as I said, the horizontal scaling. Basically think of it as, if you have a machine, you are trying to add more power to it, you add more machines, right? So that is horizontal scaling. You have one machine, so you have a network of machines. So that's the peer-to-peer network, and so you have one machine to multiple machines. And this will be heterogeneous. I mean, not all machines might be running on the same platform, same operating system. So different software. So there are challenges associated. So the second one is the vertical scaling. So installing more processor within a single machine, right? So there's more homogeneity to the environment because it's the same environment, and it's easy to build software. There's not much heterogeneity involved. But then there is some limitation, right? You cannot just add stuff to it. There will be some limitation in how much you can add to it. Right? Yes.
It's horizontal scaling where you like, okay, so yeah, so you add multiple machines, so
Yes.
like to do?
Yeah, yes,
what do you
yes,
say?
yes, yeah.
Okay.
So yeah, I will give you more. I'm just going through it because we have a few slides talking about these issues. Okay. So that's what we had here. Right? So in horizontal scaling, peer-to-peer, Hadoop, Spark, where you have one machine, and then the vertical scaling are the ones like multi-core and GPUs. Okay. So the advantage being that the horizontal scaling. So I have this slide that talks about for horizontal scaling, the scale out will be easier, right? So all we need to, so I have some data and I'm trying to process it. I have 2 machines that I can use to process it. If I start getting more data and I want to do that processing, I can just add 1 more machine, totally separately from what I already have. So upgrading to a system is not that expensive. It's much easier, right? So in terms of the so financial investment is less, and increases the performance and responsiveness. The problem, though, is because of the new machine, you want to make sure that these machines, this software, this data analysis can work in the new machine as well. So the new machine, we want to make sure that it is homogeneous to the one that we already have. Right? You cannot integrate something that has a different operating system to this operating system directly. The software to integrate multiple machines are very rare, right? So it's not many software that you can have, and software you will have to develop some of the things to make these machines talk to each other, right? It has to handle all the data distribution and processing complexities. For vertical scaling, the opposite is true, right? Because the software is easier. The software are all available. So if you have GPUs and if you have empty GPU slots, once you put a new GPU in it, in the empty slot, there's nothing much you need to do. It automatically takes into account that, okay, there's a new GPU and the software. So the software is not at all a big problem. But the main problem is that there are limitations in how much you can add. There are only few slots that you can get, right? So you can if you have a peer-to-peer network or a Hadoop or the Spark systems, you can keep on adding machines. There is some latency involved, but apart from that, there's nothing that stops you from adding any number of machines for any amount of data. So if you really have large-scale setup, even a supercomputer has its own limitations in terms of how much data it can process, as opposed to a peer-to-peer network or a Hadoop system. And we will talk about the differences between the peer-to-peer, why peer-to-peer is no longer popular compared to Hadoop, right? So everywhere people talk about Hadoop compared to peer-to-peer. It used to be popular 10 years back, but not anymore. Right? So it requires a substantial financial. It's not going to come easy. A single machine that is so powerful, it's not going to be a commodity hardware. It's not something that you are going to use it every day. Right? So those are some of the issues as to handle future workloads and initially additional performance goes to the extra. So, for example, if you have some capacity, you buy this capacity upfront, right? Maybe you don't need it that much in the beginning. So the additional power is going to go for this, right? It works either way, right? So if you need more, so you buy a lot more, but you may not need it at some point, so it's going to go there. In a Hadoop or a horizontal scaling platforms, whatever you need, that only that you will see from Amazon first at the end of the tutorial, that whatever we need only we will get it, right? All others we don't buy. So you pay for the amount of stuff that you really wanted, right? So you don't really pay for the entire supercomputer or the GPU cluster. So that's what I really mean. So the prominent horizontal scaling platforms, peer-to-peer networks, as I said, it was popular a few years back. Some data mining algorithms were also published in that area on the platforms. And Hadoop and Spark is a new platform that's coming up recently. We'll talk a little bit about that and how is it different from Hadoop. And it's kind of next generation thing for big data. So we'll talk a little bit about that as well. Yes.
So about the horizontal and the vertical, I was just wondering, for the vertical one, you have this one machine, right? So I know those are like a big machine, but I think also if that machine has a problem, then your whole system is down.
Yes. Yes.
While the other one, if it's just one, then you still can.
Yeah, but then usually in such because it's one machine,
yeah.
This is treated as such an important issue. That's called fault tolerance. We will talk about one of that characteristic as well. So the fault tolerance mechanisms in single machines are very powerful. Whereas if you just put a bunch of machines together, these machines, the horizontal scaling platforms are not meant to do fault tolerance. So every machine is its own because they know this is a very important issue. They take care of very additional importance to that fault tolerance mechanism. Okay. That's an important point. I'm going to talk about it afterwards. Any other questions? Okay. So in terms of the vertical scaling platforms, as I said, the HPCs are usually big universities or big places, right? Supercomputers, you would have heard about this thing. These fall into this category, HPCs, high performance computing clusters and so on. Multi-core is, most of the computers you are getting now is not just single core anymore. They have multiple cores. I mean, around 10s, maybe 20s cores are becoming common. 8-core machines you start getting, because you can do multi-threading and try to parallelize your own, make it more efficient and so on. So those are multi-core processors. Kind of commodity hardware, but still a little more prevalent. GPUs are very specialized units, and they are getting more popularity because the platform has become more user-friendly. People can use it for other real-time applications. They started for game programming and more video processing, these kinds of applications, but then they are now into really reaching out to many other data analytics. So in the data analytics community, this is becoming very popular as well because of the real-time power, real-time analysis power of such platforms. FPGA are rolled the platforms, not very popular in the data mining community, but they are pretty much like doing the algorithm within the hardware itself. So the hardware is a very specialized hardware but the cost of developing any algorithm into it is going to be extremely high. It's not very easy for specialized people only can. Right. So I'm not going to talk a little more about this in the. So let's start one by one. I mean, please let me see how we are doing with the time. Yes. We have a team.
Yes.
Okay. Right? So peer-to-peer involves millions of nodes. Some of you, if you're old enough, you know the very popular software called Casa and these things where you can do file transfer. I'm not sure what is the new generation. People can do from one machine to the one machine file transfers directly. So there are these node-to-node interactions, direct interactions, and the nodes can be connected directly. But to do a task that is more big data task, one can connect multiple machines and try to do the processing. The problem with such a setup is, of course, fault tolerance, right? So one node goes down, we don't know what happens. Each node is capable of storing and processing. The popular communication scheme used is very popular term called MPI, Message Passing Interface. And so people use this MPI even in the HPCs, high performance. That's why it's still out there. The drawbacks being that the communication is a major problem. From the data analytics perspective, if you see, for sending it, broadcasting it, it's easier, but then aggregating the results is not going to be that easy because we don't know which part is in which location. It's going to be quite challenging because there's no master-slave relation here. There's no one master that sends everything, and so it's just everything is peer-to-peer. And you can do. People have published some work in data mining using peer-to-peer networks as well, and very extremely good fault tolerance. If you are looking for fault tolerance, this is the last category that you want to really take, right? Because if something breaks down, the whole system will go away. So these are the major drawback because of the fault tolerance. This is almost extinct now in the data analytics community. Okay. So because of that, they have very powerful fault tolerance in Hadoop, which was developed by Apache. This is quite recent. I mean, maybe say a decade. They use in the Hadoop you have the HDFS, which is a distributed file system, Hadoop distributed file system, and Hadoop Yarn, which is the resource management. So which job should be sent where. So it's all very integrated in a very cohesive manner, schedules the jobs across the clusters and so on. So this is the overall architecture for Hadoop. If you see, this is the HDFS, the distributed file system, and then the Hadoop Yarn, which is the resource management. And we will talk a little bit about MapReduce because this gained a lot of attention in the community. Hadoop MapReduce for parallelizing the task and trying to make data analytics more applicable for big data and so on. Then there are a lot of other MapReduce wrappers or other programming languages that were built on top of it to make the MapReduce coding easier, right? So, for example, Hive is developed by Facebook. It's kind of a database, right? It's a data warehouse to get access to the data much quicker. Pig is a scripting language as well, and then the HBase, the database version, Storm is the event processor, and so on. So they built a lot of tools around this Hadoop MapReduce to make the job easier. The MapReduce is the core component in Hadoop, how the platform can really perform a parallelizing or partitioning of the data, and all these important tasks that are relevant to data analysis is being performed in the MapReduce architecture. So MapReduce architecture is basically twofold. One is the mappers part and the other is the reducer part. In mappers part, it basically reads the data from HDFS, processes it and generates intermediate results. The reducer takes these intermediate results and do the processing and then writes it back to the HDFS. So this is one iteration of the algorithm. You take from the mappers, from the HDFS, the mappers will get some of these things. I think I have one more slide on this. So this is from the computing terminology, from the computer science terminology. This follows the divide and conquer strategy. You have the workload. Workload is now into three mappers. These are the mappers, three workers. We call it as different names. Each worker it does process on its own data. So the data basically, if you can think of it, this workload is being partitioned into three portions of the data. Each worker has its own portion of the data. And so that is the partition phase of the thing, or the mapping phase, where individual mappers, and you can think of these as totally independent commodity worker, just a small CPU, just a regular computer that you have it there. So each worker processes it and it prepares its own intermediate results. We will talk about this in k-means, how we are going to do that. What are the intermediate results, centralized computation. We will talk about all that so that you will have a more complete understanding of what I'm saying. I'm just giving a very high-level overview of all the platforms at this point. Right? And then the reducers will take these results. Maybe we may need only one reducer or two reducers. So the reducer take these results and then builds the final result, and then it's written into the this. So this is the combined. So the partition. So this is the divide and conquer strategy, where you partition the results, individual results, you combine and find the best result out there. So this is the MapReduce paradigm, which is very popular. Yes.
So what the one scale is handled by.
Yes. So Hadoop has extreme, very robust fault tolerance mechanism that even if one workload fails, it takes backup and gets the workload done by some other workers as well. So it does the job scheduling. In case of failure, it has the software that takes care of doing the multiple locations, backup machines and so on. So that, and as a user, from the user's perspective, you don't have to know anything about, and you can just rely on the system because there is always very good failure fault tolerant mechanism back end. That's one of the main distinctions of the Hadoop with peer-to-peer. Of course, here you can see that there is one master person who distributes the work, so everything you know where everything is going, as opposed to a peer-to-peer network where this is not very evident from the peer-to-peer network. Yes.
But is the reducer somewhere tell how many times we try, wait for my all complete or wait for partial? Then
see, I worked in Hadoop 1 before in 2008, but in 2012, looks like there is new Hadoop version. In new Hadoop version that was released, Hadoop Jan 2 or some version, you have a lot of control. In the original version of Hadoop, there was not much control. Okay, the system does, and sometimes all the nodes, even though you tell to get to 20 nodes, if the task can be handled by 2 nodes itself without losing much efficiency, Hadoop does that. Right. But now I think there's more, we have a lot more control in the new Hadoop version.
The second layer.
Yes, yeah, the resource management layer that takes care of all the fault tolerance. Otherwise, the HDFS as such is a robust distributed system, but it has to know where the resources, how to allocate the resources. There is a huge work on that area. Job tracker wants to know if each and every job, where it is, what is the status, and how long it's going to take, and so on. So Apache Peak and Thrive, we will talk about it. Okay. And the Spark. So one of the main drawbacks of Hadoop, this really built on the drawbacks of Hadoop. This once again is a horizontal scaling platform. The main drawbacks of Hadoop is the fact that once you are done with partition and combine, if the algorithm needs more iterations, right? We'll talk about that in k-means. But the idea is once you write the result in the end of data, that is just the result of one iteration. For the next iteration, what happens is now the HDFS, it goes back to the mappers and then does the partition and combine again. And you write to the disk, and then it goes to the third iteration. So each iteration, you are reading from the disk and writing to the disk. Because of that, the system becomes very slow. So for iterative algorithms, Hadoop platform is not the best platform. And whole Bay Area started working in this platform Spark, wherein it was built in the University of California, Berkeley by the group of researchers. The idea is that after you combine, after you get the results, don't write it to the disk, store it in a memory, and then you read it from the memory again. So you avoid that writing and reading from the disk, which is the most expensive process in the big data in the context. So you avoid that part, and so they built their own stack of layers and their own programming languages to help do everything remains the same from Hadoop to Spark, except that it is more faster. And some applications it has been shown 100 times faster in some of the data mining tasks because you avoid writing and reading from the disk. Writing to the disk and reading from the disk doesn't exist in Spark. It has its own special memory wherein it tries to write, and usually, as you know, memory is much faster accessible than writing to the disk. Okay, so that's the main distinction between Hadoop and Spark. Yes.
I'm having a hard time to understand, for example, which application of machine learning can work better in Hadoop rather than Spark.
Yeah,
for
so
me, it's like optimization function that we optimize.
So in terms of any algorithm that is iterative, will always work well in Spark. Because the main advantage of Spark is writing to the memory and reading to the memory. Right? So if you have an algorithm that is iterative, always Spark will win.
Can you name an algorithm that could work better in Hadoop rather than Spark?
No, it's very difficult. There is no one specific algorithm. There are some advantages in terms of the robustness because hard disk is more reliable than memory. There are very minor advantages, but at least there is no work existing that says, okay, for this particular algorithm, Hadoop. We basically can see this as a Spark is the next generation of Hadoop, right? So in that case, yes.
Okay, so how about with the volume aspect of the four beats, right? Because I mean, you can only have so much memory, even when you replicate across many machines, right? So,
yes.
So is that how much of that is a impediment for wanting to Spark? Or does Spark always figure it out somehow? Do they put some to HDFS and use the rest of
the existing memory is not sufficient, then it tries to HDFS. Okay, they don't call it HDFS, but they have their own file system that basically does, to limited extent, it does in memory. But then they have this hard disk as a backup. Even in that case, you are writing less to the disk compared to the Hadoop system. So even in such applications, it's known that Spark is going to.
And how much memory do you usually have? How much RAM do you have per node?
That varies. I mean, it's system dependent, right? Whatever you have, once you install Spark, some memory is allocated instead of the disk to take care of that. Right? So you get, we can show that different platforms we can control in Amazon Cloud Computing environment the memory hard disk that you want to allocate for each of these platforms.
Okay.
So depending on how much you need, you will have to pay in the cloud computing. So you control those things. Any other questions? Okay, so that is about Spark. So these are the three horizontal scaling platforms. And now we will talk about the vertical scaling platforms, right? So the HPCs contain well-built hardware optimized for such applications. So as I said, the fault tolerance, everything we are going to talk about the vertical scaling, because they know this is the only single machine, right? Homogeneity is good, so that's a positive. The limitation for the large-scale data, if you have trillion data points, right? Not the platform. Maybe best supercomputer might handle it, but any HPC or multi-core, no, it has its own limitations because it's a single machine, it's a single capacity. You cannot add more power to it that easily. Okay, so that's the first thing that you need to. And cost of scaling up will be very high. Initial cost of deployment is high. So those are the important points. And so these are not as scalable as Hadoop and Spark. Fault tolerance is not equal because top quality high-end hardware, right? Because most of these machines, they know fault tolerance is a very important issue. The hardware they use is not the standard hardware. It's a very high-end machine that is very robust to any kind of top, say any kind of fault. And the LPI message passing interface is the common communication, the programming mechanism that happens. Right? So multi-core, most of us will be familiar with it. It allows for multi-threading. I mean, it has multiple cores, so that it's not just you can do things parallelly by using multi-threading concept. Most of you would have heard about this multi-threading concept, how to write in C programming and so on during your undergraduate studies and so on. GPUs are kind of very specialized. They started, as I said, with other very specialized applications. Now, because of its popularity in real time, it's gaining more. It's coming more to the mainstream applications in most of the applications. The main difference is that it uses very special memory called DDR5 compared to a DDR3 memory, which has more memory bandwidth. So the memory capacity of GPUs is much higher. So it has its own processor, and I have a slide comparing CPUs and GPUs. And CUDA, NVIDIA is a company which comes up with the CUDA programming framework. which simplifies a lot of GPU tasks, right? So some of the coding in GPU, which is very cumbersome. That's one of the main drawbacks of GPU, that if you have a C code, converting to Hadoop is not much difficult compared to a GPU. GPU code, you have to write everything from scratch. It's a very difficult code to write. And because of that, they haven't been so popular. The libraries that you have for doing some of the basic data analysis tasks are not that many. Everything you will start writing, or think about it, if you don't have the C library, right? So CUDA came up with nice framework. Recently, it started to come up with a lot of library files that can help in the basic data processing. So CPU, you can see 4-core CPU versus say 14 multiprocessor, each multiprocessor. So the GPU structure looks like this. Each multiprocessor over here has 32 cores in it, and it's very powerful because of memory bandwidth and a lot more processors. Not as each core is not as powerful as this core, but still it can do a lot of minute tasks. And we will talk about it in the gaming algorithm. What is a minute task and how this process do the work in computing the closest centroid, for example. We will talk about that in just keep this place in mind. So in terms of CPU, as I said, is still in double digits. The growth in CPUs, if you look at the last 5 years, and the growth in GPUs are not comparable, because GPUs have been growing very fast. The programming has become a lot more easier. It is very tough to program in GPU. It's not that easy. There are special courses that teach you how to program in GPU. So that is that intensive. Not like a standard C or a Java program. So GPU programming is much more harder. Right? So CPU relies on system memory, which is much lower than the GPU memory. GPU bandwidth, DDR5 memory is much faster and slower. GPU is appealing option for parallel computing, number of software applications and advantages is data. So this is the thing I mentioned. So FPGA, as I said, there are these very specialized security applications wherein you basically try to encode your algorithm more into the hardware itself, right? FPGA is a field programming array where you try to, you have very, it's called HDL, the hardware description language. You try to code it in the hardware language, as close as getting to the assembly level or more difficult programming language. Very rarely used, not much, especially only when you have very specialized cost. The problem becomes, if you want to add anything new to it, it becomes very difficult because it's already completely installed in a hardware system. It's not going to be easy. It's not going to be easy to modify the code and stuff. So that is about FPGA. So this is where we stand. We started with scaling, the big data platforms. Scaling is very important. And so horizontal scaling, vertical scaling. And now we will try to compare all these platforms with different characteristics, which are very suitable, which are applicable in the context of big data, right? So in terms of the characteristics, as I mentioned, the first, if you remember the first few slides, you have some questions that which are algorithm dependent or system dependent, right? The system dependent questions are regarding scalability. If you have the setup already, if you have the machines, if I want to add something new, is it easy? For some platforms, obviously for horizontal scaling, it becomes much easier than vertical scaling. Right? So that's the first point. Data I/O performance. For example, if you have multiple machines, how is the data transfer between them? How fast is it? Or if you have from memory to the hard disk, how fast is the data transfer mechanism? And so on. Fault tolerance. Right? If something fails, how robust is the system? Can it still handle the things that the machine without the machines that fail? Right? And the real-time processing, how quickly can I get the results? Right? Real-time, how fast? Right? And you can see these are algorithm dependent. So application, if the application demands you to have a real-time analysis or a real-time requirement, then there are only certain platforms that are more suitable. And then the data size support. Platform has its own limitation. Each of the 7 platforms can handle only some amount of data, right? Exabytes, terabytes, petabytes, gigabytes, or just megabytes, right? So what is the upper bound of how much data size? If your goal is, okay, forget about real time, forget about fault tolerance, I can do all that on my own. All I care about is I have petabyte data and I just want to get the results whenever I can, what is the best platform that I, so it depends on your application. What are some of these characteristics you can think of? And if you can think beyond these characteristics, please let me know, because our paper is under submission, wherein we summarized all the characteristics and all the platforms. We have a comprehensive survey paper, and which is under review. And so if you think of for any application, because we thought very comprehensively all the platforms, if you have any other platform or application, which I hope you don't find, but if you do, please let me know, please email me, okay? Because that's one of the, because I want this to be, everybody, at least in the data mining community, people talk about algorithms, they talk about scaling algorithms, but I think understanding all the platforms and characteristics at a very high level is the first step before you think about the analysis algorithms. If you have the data, don't think about the algorithm first, but think about what are the characteristics in the application problem that you really need before you even think about the algorithm. Data analysis is just one final step to do the process, but in the process you need to understand more about your requirement, what are the most optimal choices, what are the platforms available, and there are many things that you should do once you have the data and application in hand before you think about what is the algorithm, because there is this tendency for the students to just jump into the algorithm. Okay, can I apply k-means or hierarchical, right? I mean, that's not what we try to address in big data. In big data, there are many other challenges that are beyond. Whether you apply k-means clustering or hierarchical clustering is the last step that you need to really worry about. And that's the message I really want to you to get out of that tutorial, that there are many other issues in big data. Before we think about the actual algorithm, we have many aspects that we need to keep in mind. And these are some of the main aspects that one can think of, or one need to think of in the data. So comparison is done in star ratings, and 5-star means the best possible, and this is the summary. Right. So for all the platforms, I have the platforms as rows and the characteristics as columns. For all the platforms, I have slides for each of these ratings, and I will quickly explain why this rating is given for this particular platform and so on. Right. We will talk about it, but in overall summary, this is how we see compared to other. And of course, 2-star here is not comparable to 2-star here, because this measurement is very different from this measurement. Just it's a comparative scale. Not really. It doesn't mean that okay, this is twice as good as this. Just that if I have to rank them, if I have to rate them, I will give 1 star over here and 2 stars. Just to keep it clear that what we really mean by giving stars to this to these platforms. Right? So now we can talk about why we are giving these stars. I mean, what makes it very suitable for this applications. So scalability, right? So how easy is it to scale up the system, right? Obviously, the heart-centered scaling platforms all get very good score, right? It's very easy to add machines, no problem. So if your goal is to just scale up the platform system, right? If you have bought already a system and you want to scale it up to other to handle more processing later, it's very easy to scale. Other platforms, vertical scaling, not so. HPC is known to scale up more because it has more capacity. It's very specialized hardware and so on. Multi-core and GPU has limitations in scale up. It cannot scale. The system cannot scale up very high. They're mostly in a single machine and so on. FPGA is hard to scale up. Right? Once you deploy it, you forget about scaling it up. It's done, right? It's like you are sealing it basically. So whatever scale up you gave in the beginning, it's not going to be easy for you to change the scale up capability of FPGA. Okay? And that's the reason why you get this range. Okay. Clear? Anything you stop me. Okay? I assume everybody is nodding their head, so nodding means I'm assuming you're getting that. Right? So at least please stop nodding if you don't understand. That way I can assess that. Okay, maybe I have to repeat certain things. Okay? So assuming that that's the standard assumption that I make. Right? So okay, so the data I/O transfer. So the rate of at least the data is transferred from peripheral device. It can be between machines, between nodes in a cluster, or between memory disk, read and write performance of memory disk. Because everything is written in network. Network is the slowest that one can think of. So there are 3 levels of data access. Right? One is from 2 machines you are in between a network, internet or any network connections. The other is within a machine you have hard disk and memory. The other one is just writing within the memory. Of course, anything you do in the memory itself is much faster. Right? I assume you all know that memory to disk writing brings things slower, right? And of course, if it's from one machine to the one machine connected in a network, that makes it harder. So in terms of peer-to-peer, this is the worst because of the slow network communication. And then, and in general, you can see that the vertical scaling platform will do better in this category because it's only one machine. Right? Either you write it from the disk or memory. These are much better than doing in a heterogeneous environment where you have up to multiple machines on this. Right? So virtual clusters have slower disk access. And the Spark avoids this problem by disk access because it tries to write as much as possible into the memory itself. So it makes the process faster by writing into the memory rather than disk access. So it reduces the disk access. It's still the problem is there, but it's not as bad as the Hadoop environment. Right? So, and in terms of HPC clusters and multi-core uses system memory usually within a single machine. But GPUs and FPGA, even though they use memory, that memory is not system memory. It's DDR5. It's a very specialized memory with very high bandwidth. So these are very good in I/O transfer. The rate at which the data is being transferred is important for certain applications. So these are once again system dependent, not algorithm dependent. We'll come to the algorithm dependent in a minute. Fault tolerance, we talked about it. Fault tolerance is where if something fails, so the definition that we gave is the characteristics for the system to continue operating properly in the event of failure of one or more components. Right? Obviously, peer-to-peer is very powerful. No fault tolerance mechanism and use of commodity hardware makes them highly susceptible to system failures. Right? So it's just standard machines that you put together. One thing fails, everything you have to have inbuilt fault tolerance mechanism, because fault tolerance is an important problem. Even beyond data analytics community, it's even generally management of data itself. So there is a very good inbuilt fault tolerant mechanism available for all the virtual clusters or all the future generation machines. Hadoop, Spark, everything has very good fault tolerance mechanism. In terms of the other platforms, the vertical scaling platforms, because they know this is a single machine, they have very good specialized hardware that are not very highly prone for fault tolerance. Right? So these are very powerful machines and they don't break up very easily. Right? So that's what we mean. Don't have state-of-the-art fault tolerance mechanism. These have most reliable and well-built hardware, which makes them makes hardware failure then extremely rare because everything is homogeneous. You have complete control. Everything was built in very good using well-built hardware. Real-time processing. So let's take the definition: to process data and produce results quickly within certain time constraint. This is the poorest. In general, these are the horizontal scaling platforms are very bad in real-time processing. If you have the data, you want to process it, and you try to get the results in real time as fast as possible, you need to go for vertical scale. So there is a trade-off. Essentially, in big data, there are two components. One is the size of the data. The other is getting in real time. These two don't go well in the platforms. That is one of the main summary points that I want to give. That if you want very large-scale data, GPU cannot handle it. And if you have very much real-time requirement, GPU are the best, but the other horizontal scaling platforms do not. So these two, which are usually spoken a lot in the big data community, are kind of contradicting concepts in the terms of platforms that we are looking for, right? So horizontal scaling is very good for the scaling up, scalability, but very poor in real-time analysis. Whereas vertical scaling platform, especially things like GPU and FPGA, are the best in terms of real-time capability, but not as good. So HPC and multi-core are also good, but not as good as the GPUs and so on. Right? So we are almost there. Then we have to get into the analytics part. So this is the first part is almost getting over now. So the data size supported, peer-to-peer, the best, right? More data is usually seen in horizontal scaling. You can add you have tasks done and you have already algorithms, everything set up. You need more data, no problem. You can easily add things, right? But more data is okay for HPC, and multi-core and GPU and FPGA do very badly for more data. Once you have this setup, it's very difficult to have them process more data with the same efficiency that they did before. Right? So this is about the data size that a system can process and handle efficiently. Usually you can even name the terms. I mean, this is in the level of petabytes. This is usually the level of hundreds of terabytes at the max. So, and then this is in terms of this one is very limited. I mean, maybe a few hundred gigabytes at the max. That's the most recent GPUs can handle only a few hundred gigabytes at the best. So finally, the other important point in data analysis, especially for the analytical or modeling algorithms, whether you do iteration only once or you have multiple iterations that need to go. Right? So in terms of multiple iterations, so because of the network communication or the hard disk writing, these two are not very ideal platforms. Because it's writing into the memory, it's fine, it's okay, it's better than Hadoop. And then all the remaining ones, all the suited for iterative processing cannot be implemented by each of these processing platforms. Okay. So this is something we can discuss. So this is the first part of the tutorial. I hope, yeah. And so now the second portion is the big data analytics, so algorithms. So this is all about the platforms, and we will talk about how these platforms. So as I said, the peer-to-peer. So in Amazon cluster in cloud computing, we have Hadoop, Spark, GPUs, and multi-core. Okay, the HPC and FPGA is not available. Okay, so because of that, we are not comparing. FPGA is forgettable. I mean, the FPGA. HPC is available to many big companies, big universities, and so on. But we are going to have comparisons. All the codes available are for these four platforms. Okay, and then we will talk about the analytics on Amazon EC2. We will discuss a little bit about. Any questions on the platform? So because we are done with the platforms, and yes.
Yeah, when you describe GPU programming, and if you have simple applications, the issue is when you have to share the shared memory so that the results from each code needs to be transferred to main memory, right?
Yes.
So it's kind of a bottleneck when you have larger data sets.
Yes.
So do you know if the new generation of VR have improved that?
So, I mean, there's no direct solution to that. That's not easy, right? I mean, but the very good, interesting problem that we had been thinking, or people are looking at it at this point, is cluster of GPUs. Let's replicate Hadoop, because Hadoop has its own advantages. GPU has its own advantages. Can we combine GPUs and Hadoop? It's not easy. It's not just two people cannot just sit down and do this. But it has its own benefits, so why don't we combine? So that way it solves the limitation. The GPUs, I see the main problem is that it's not scaling up. But if you have clusters that you can easily scale up, can we combine the GPUs with Hadoop? That's one of the interesting directions that people are taking, okay, to avoid the problem that you have mentioned. Okay, so let me go through the algorithms. So the basic algorithms, as I said, I mean, if we don't have time, I mean, we can take the demos, everything offline. We can do. I will show what the demos are. But I want you to make sure that you get the algorithms, because just running the code is not enough. You need to get what is inside the code eventually, right? So you need to understand what goes on into the code and so on. Right? K-means clustering, let's start with the basics, and then I will talk about, because this is very important, because these two algorithms I chose, because of their popularity, their simplicity in the algorithm, and most importantly, you can think of any of your algorithm and see if it's an iterative algorithm, if it's a distance computing algorithm, if it's a centralized computation algorithm. These things are, you can transfer your problem into these problems very easily. If you have more data, how do you do it for multiple GPUs, multiple things? How do you make it faster when you have multi-core processing and so on, right? Or in Hadoop, how does this work? So it's very important that you thoroughly understand K-means on all these platforms. When I mean all these platforms is the parallelization component, the idea is very similar. Just that in Hadoop, you do it in a map-reduced fashion. In GPUs, you do it in CPU-GPU communication. In multi-core, you do it between cores. So we will talk about all those things, because any of your algorithm, I'm not going to say, okay, you need only K-means in the future, right? But any of your algorithms, you can think of it as transforming that requirement into the things that you already know. So it's very important to know what some of the basic algorithms, how they are on these platforms. And that's what I'm going to explain in the next 10-15 minutes. Okay? Yes.
So before we move to algorithms, so on the infrastructure side, yes, you had Spark, Hadoop, and peer-to-peer systems. So where do things like traditional databases fall in
You see, databases from the system's perspective is just one layer on the system. The platform is more at the hardware level, right? So the next to the hardware is the platform, and databases is kind of is what sits on, like data analysis sits on the platform. Database is something that sits on the platform. Okay. So k-means clustering, just to give a brief demo, the goal is to group the points together. You start with, so assuming that you know how many clusters are there, you start with random centroids. So these are the random centroids. So we selected these three and compute the distance from each of the points to the closest centroid. Right? To compute the distance for each point to each of the three centroids and pick the closest one. You assign that point to that centroid. I'm repeating this because even though some of you might not know, but even if you know, these what can be parallelized in my explanation is what I'm going to talk about in the next slide. Okay, so that's why I'm repeating what I'm really doing in k-means. Because if you know k-means, don't think, okay, we are done, right? Because this explanation is very important to understand what aspect of this is being parallelized and how it's parallelized. Okay, so that's what I want to keep attention on. So every point you compute the distance of the closest centroid, which means you compute the distance of all the three centroids and pick the closest one, right? And then you assign that point to that centroid. Right? So for every point in one iteration, all the points are assigned, are computing the distance to all the centroids and picking up the closest centroid for each point. Right? And then even within that iteration, the centroids are being updated, which means once I have chosen all the green points, so these are all my green points, I can compute the centroid of that. So now that, so this point, I made all the assignments. For all these green points, the centroid is going to be somewhere over here. For all these blue points, the centroid is going to be somewhere over here. For all these red points, the centroid will be somewhere over here. Right? So once you make the assignment, the centroids are being computed, right? And that's the recomputation of centroid because I started with the random centroids in the first place. And now I'm recomputing the centroids based on the assignments I made. So this is done in one iteration. Right? Once you have this, right? So this is my new centroids. The new centroids, I am assigning the points that are closest to this centroid. I assign the points in blue, all the three clusters, and I'm recomputing the centroid. Now you can see the number of red over here increase. So that's why this centroid is going to move over here. Right? Number of green over here reduced, and so this is going to move. This is going. Basically, in this example, this cluster is pulling this centroid, this cluster is pulling this centroid, and that's what it gives. As these are iterative, this is happening iteratively. So each iteration, you're computing the centroid distance, and then you're recomputing the centroid. These two, you are doing it again and again, and that's how eventually this is the final cluster that you will end up getting. So this is a very simple algorithm, but it has lots of distance computations. Right? The goal of this tutorial or the big data analytics part is what if I have trillion data points, billions of data points. Each, if I have to do on a single machine, it's going to take forever. You can see that distance computation is easily parallelizable because the distance of this point to this point is totally independent of this point to this point. And that's where the big data platforms can be really helpful. Wherein if you have multiprocessor parallelizing this code, the distance computation, which is a very critical component, it can be done parallelly in multiple ways. Yes.
So do you come to do more than one run?
Yes, because usually you won't get convergence to, it's basically a local optimum in the objective function. So you'll have to keep on iterating, and it's not like you need hundreds of iterations, but you may need tens of iterations to get the final solution.
So that could be even longer. That could be even longer since you have to do it more.
Yeah, and especially because of that, Hadoop is not the right environment because every iteration you have to write back the centroids, the new centroids you computed into the disk, and then you read it from the disk. Right? That's where the Hadoop is really bad. So that's when we have the iterations. Then it makes it very time consuming. Yes.
If you have an idea of like how your data clusters, can you use can you randomize but within like certain parameters? Would that be?
It can make it faster, but we don't have an idea, right? That's not very easy to. Maybe in your application you might get. If you have more knowledge. But what I'm going to explain is just in the normal setting, right? When you don't have any knowledge, I mean, if you want to make even this faster, how does a GPU work and how does a map reduce work is and will explain. But I agree that if you have more knowledge on there are many methods on improving k-means algorithms, but how it is really done in a platform level, there are not many explanations, and that's what I want to give you in that. Right.
It's fine, thank you.
Okay. Right. So if you look at the pseudocode, it's a very simple algorithm. So basically, you start with as if you know the number of clusters, which most applications we may not know, and the number of data points is usually given. So initialize k centroids randomly. You pick some random points and you make them as the initial centroids. If you have more knowledge, we can pick more intelligently the centroid, but we will not get into those aspects. Right? And the steps 2 and 3 are the ones where the iteration keeps on going. Associate each data point to the nearest centroid, and the data points will divide into k clusters. These are pseudo clusters because this is just the result of one iteration. Eventually, these converts to the real clusters that the algorithm can get, right? And recalculate the positions of the centroid and so on. So those are the main points. Right? The reason why we chose is, of course, the popularity of k-means and the simplicity of the algorithm. But yet, there are very important characteristics that are commonly seen in many other data analytics applications or data analytics algorithms. Right? So some of them are iterative nature of the algorithm. So this explains exactly if there is an iterative algorithm, how is it being handled in a GPU, how is it being handled in a Hadoop, or how is it being handled in a multi-core or Spark, and so on. So that's the iterative nature. There is this compute-intensive part of calculating the centroid. So centroid computation is not trivial because you are talking about if you have billion data points, some of it can come to one point, and you are trying to compute the average, and you are trying to do the compute intensity. And most importantly, what aspect is parallelizable? So if you have a parallel setting, how do you aggregate the results of individual nodes or individual machines to get to the final? This is very important because this is commonly seen that you aggregate the local results to obtain a global solution, then the algorithm is parallel. Right? How do you aggregate that? So these are very important aspects of k-means that are more widely applicable in other applications, other algorithms than the standard, than what you might think. Right? So I'm providing a pseudocode of GPU. I think going step by step might be tedious or difficult. I have a picture in the next slide, but this is the pseudocode just if you want to see everything in single slide. So this is what happens. Right? So in gaming, so you start with the CPU. So you have the CPU and GPU. So most of your CPUs these days are coming up with having GPUs as well. Right? Initialize k centroids randomly on the CPU. You have the data. You choose random centroids, so that can be done within the CPU part itself. And then the GPU is the specialized portion. Right? So what happens is these centroids. So so the data is sent to the GPU. Right? The data is partitioned. So let's assume I have 10 GPUs here, and let's assume the data I'm setting is 1,000 data points. The 1,000 data points go over here, and only 100 of them in one first process, 100 in here, 100 in here, and so on. Right? So 100 in each processor of the 10 processors of GPU I have. The centroids are available across. Right? So each processor computes for each data point what is the closest centroid. Centroid, remember, typically it might be 5 clusters, 10 clusters. It's in the order of tens, right, at the max. So each processor will compute the distance of the centroid, each of the centroid to the data points. But the data points are partitioned in this manner. Okay. So once you are done with that, now remember, I want to choose only the closest centroid. Right? So each processor computes the distance point at a time with each centroid in K. Associate each data point to nearest centroid. So that is the next step, that you find the nearest centroid. Yes.
So each GPU has the data it has, and then the feed, if you have more than this and
yes, centroids, just the centroids, right? Yes.
So you sent all of the centroids, but you partitioned the data. Why wouldn't you, or is there a case where you would want to send all the data and partition the centroids?
Partition you're picking randomly centroids. You're not partitioning the centroids, right?
No, but once you have your random centroids,
yes,
would you want to assign a different centroid to each GPU? And have it do all the work, but just for that centroid?
No, because that's not easy. I don't know which data points. First, I have to compute which data points have to be. I don't have the knowledge of the centroid at the beginning, right? So the only way to do that, that's what I mean. People, we think it's very trivial, but when you have this, so think about it. You have all the data. We have the centroids. We don't know which of the data. The goal of this first iteration is to find out which of the data is to this centroid. So in this problem, the obvious thing to do for partitioning is to partition the data, because we don't know the assignment yet. Right? So now you can appreciate why k-means people think it's so easy. Obviously it is easy, but it's not very trivial when it comes to parallelization platform. Right? But this is what I really want to get from this tutorial. I really want you to understand how the partitioning is done, because this partitioning plays a critical role in big data. People talk about real time, people talk about other things of big data, but having multiple processors, the main advantage is the parallel processing. I mean, there's no question in that. Is that clear? So the data is partitioned. So the data in each partition, I also know the centroids. By GPU global memory or each processor will know the centroids. Actually, the GPU has a global memory, the shared memory. That's one of the advantages. I'm not giving all the details, but the centroids are in the memory of the GPU shared memory, and then the centroid, each processor has its own data points and it's computing from the shared memory, right? The data points. So now it becomes easy to, once I have computed all the centroids distance, it becomes easy for me to compute, to get the closest centroid. Right? Why do I need to close this centroid? Just because I want to assign the data point to that centroid. Right? So now each GPU, each point exists in only one processor. That's important to know. And each processor, it has assigned the nearest centroid. Now when you go back, so now what happens is in the next step, this association of data points to the centroid. Remember, this is still in the first iteration. We are still in the first iteration. We just assigned the data points to the centroid. These are not the final clusters yet. This is just in the first iteration. We have made the assignment of this data points to the centroid. You send the association back over here because the centroid computation is very computing intensive, which means if you have billion data points, half of them are one cluster, half of them are the other cluster. I have to take a billion data points, half a billion data points, and compute the centroid. And that's not as easy as what we think, because computing the centroid, if you have 2 points, it's an average, right? So if you have half a billion data points, it's a very compute-intensive task, and this task surprisingly cannot be handled by GPUs. And that's the reason why the partition and assignment has to be sent over here. So the k-means, if you want to make a centroid computation, that has to be done in the CPU. So that's why it's called CPU-GPU communication scheme, wherein some part of k-means, the distance calculation parts are done in the GPUs, and the centroid computation part is done in the CPU. That not many people really know that part. Okay, so that's what I want you to get.
So
yes.
what is sent back? Just the mapping?
The association for each data point. Each processor can send back the association it made, just the closest centroid. That's enough for me to recompute the centroids in the CPU part.
And is the time from the CPU to the GPU that
it's a single machine, right? It's almost like memory to memory. GPU is kind of a specialized memory. I think of it. It has its own memory bandwidth. It's a specialized hardware, but it's very fast to transfer data from GPU, because this is all one machine only. It's not multiple machines as opposed to the. Okay. Yes.
Can we do the computation on, instead of doing on CPU, we ship it to GPU? Is there a lot of requirement synchronization or some formula?
Can you be loud? I can't.
Yeah, because after you compute like the distance and this associated with central point, we send it back to CPU?
Yes.
Or like compute the central?
Central, yes.
Instead of doing that, can we like put everything on GPU?
That's the point. Each processor doesn't talk to each other. Only it can discuss with only through the shared memory, and that doesn't have the potential to handle everything back and do the computation of the centroid, because this is very compute-intensive task, and only CPU portion can handle that. Because if you have half a billion data points and you're trying to take average of it, that's not a very trivial operation that GPU can handle. That part GPU cannot handle. And this part is really for parallelization. Okay. So we compute the centroids with the given association to CPU once it computes the centroid. Now send the new K back. Remember, the same data lies again. So the data is not sent. So it saves a lot of time. Once you do the partition and sends in the first iteration, The data remains the same. Data doesn't change. Only the assignments change. To change the assignments, all I need is new centroids. So all I do is just send the, once you recompute the centroids in the second iteration, I send the centroids here and the assignments back over here. The data, once it's sent once, that's it. So both CPU and GPU has the data, but you don't send the data back and forth. You send the centroids here, get the assignments here, and you just iterate it until it converges. Right? Yes?
And what to do if you don't have enough memory to store all the data going to GPU?
Oh, that is different. That's what I mean. Scaling. I'm not talking about scaling up. Scaling up is a problem, right? And it has a limitation. It has a limitation. So I'm not saying. I'm just saying how this handles the parallelization. But that's a very good question, and that's what it's for scaling up purposes. The GPU is not there. But in terms of fastness, this is as fast as it gets because I'm going to talk about MapReduce and multi-core thing, but this is the fastest because it's really because of the parallelization power. If you have cores. 10 cores, right? The parallelization power is limited, right? Whereas multiple cores, I mean, we are talking about 2,500 cores, for example. Right? And the distance computation is easy. You have 2 points, you are computing the distance, Euclidean distance or the cosine similarity, whatever distance. It's just between 2 points you are computing, and that's where the power of GPU really is.
Yes. Did you say that you got 2,500 cores where?
No, multi-process within GPU. So the number of cores is, even if you buy a standard GPU, it's like 1,000 cores. If you have a expensive one, it has like 2,500 cores. It's becoming very common. Okay. So then repeat 3 to 6 until convergence, right? Same thing. So, because once you did the data, you get the assignments back. So you did compute the closest centroid. So 3 is closest centroid, assignment back, computing centroid, send back the new centroid. This process until you see the centroids have converged, you are going to do that until that. So if you didn't understand anything, please let me know. I am happy to repeat this because this is the most important thing that I wanted to get from this tutorial. Everything else follows this thing. Yes.
So on the final step, when you have all the data with their final centroid, you send it back to the CPU. Does it compute it and put each one in the cluster?
Yes. So ultimately, k-means result is going to be which cluster it belongs to, the association, right? So once you have that, I mean, you know the centroid doesn't change. You don't even have to send back to the CPU, right? You are done with it. Yes.
I know that they're doing big systems with ARM architecture because they have like now multi-core GPUs.
Yes.
And they're really integrated closer than they are in the CPU and GPU in a normal system. Can you scale with the ARM architecture and be faster?
So, I will do the MapReduce, and we can take that question after I do the MapReduce. So we will explain the same process in the MapReduce architecture, how the MapReduce handles it, because that's also very popular. How MapReduce and Spark, everything falls into the same category. How it's parallelized in the partition combined mechanism, the same computations. And then probably we can take that question at that point. Right? And also I will talk about multi-core also. Yes.
No, I was just wondering. So because I know the assignments, so the CPU has a copy of the data, or it has to ask for it back.
No, CPU has the copy.
CPU
has the copy. Right? Once you get a new assignment, CPU copy of the data. So the data is sent only once to the GPU. Okay, so let's go to the other one. So this is the multi-core. Multi-core is kind of very similar to GPU, except that we don't have that many to parallelize. I mean, we have only maybe tens or 20s of cores. The parallelization works in a very similar manner, just that it's not GPU, it's not a separate one, it's within the core itself. So it's very simple. It's very, once you understand GPU, multi-core is not going to be a big thing. So if, for example, if you have the core and you are doing initializing the centroids in the one core, you have the data, you have the processing. Then you send the centroids and split the data into multiple cores. Just like what you did in GPU, you divided the data into different processors. So you divide the data into different cores and then associate each data in D with the nearest centroid. So this is what is done in GPU, and then send back recalculate the positions of the centroids, and until there are no more changes in membership. So this is the same thing as GPU, except that we have fewer cores. It can be programmed very simple, multi-threading, very simple. Programming wise, it's much simpler. But scaling up wise, or it doesn't have the GPU level of parallelization because you have only limited number of cores. Okay. Very simple, very similar to the GPU setup. The other hand, MapReduce is different. Yes.
Are you picking one of those, say, 4 as the master?
Yeah, you can do. People do it different ways. You can do it with that, or you can just do, because each core is equally powerful. You can just do the centralized computation. Each individual one has its own local copy of the data. You can do it many ways. There's no one standard way that one can really do that.
But I figured that you would need still one process to go through all the data to be
Yes,
able to.
but then each core is equally good, right? To do it.
Okay. Yeah, each core.
Yeah, so it's all the same. MapReduce is something I want you to get as well, because not only for K-means, because MapReduce, how many of you are aware of MapReduce or did some coding in MapReduce? Right? It's one important aspect that you should learn if you are going into big data or many people, I mean, many companies would want you to know MapReduce. It's a very good tool for you to have in hand, right? So let's see how K-means works on Mapper in general. Whenever you are using MapReduce, you partition the data into different mappers. Remember, this is Hadoop architecture we are talking. Let's say Hadoop or Spark or anything where it's a horizontal scaling platform. We have several machines together. Each machine has its own version of the data. It has its own partition of the data. Right? So copy D, K and D to the memory and initialize each centroid with 0. Okay. So each mapper task compute the distance to each point and with centroid array, assign data points. So basically, whatever you did in multiprocessor within that GPU, you do that in each mapper, right? But each one has its own centroid array. This master that sends all the information over here. It partitions the data. It sends the centroid, the current randomly chosen centroids. And now output the key value pair. So now the tricky part over here, or the different part over here, is that the key value pair with the key as the centroid. So each mapper, the intermediate result in MapReduce always is a key value pair. The key and the value. Right? So now what happens here is that the key is the centroid. So for each of the centroids, it assigns. So let's assume I have 10 machines. I have 1,000 data points. Each one has 100 data points. Let's say I have 2 centroids. For each centroid, I know what are the data points associated with that centroid. Which means for every data point, I computed the distance of each of the 100 data points. So this node here has 100 data points and 2 cluster centroids. So for each data point, I computed the cluster distances, the centroid distances, and I chose that, okay, this is cluster centroid 1 is my closest centroid. So now at the end of this part, each data point has a cluster centroid assignment. Is that okay? Right? So now the result of it will be in a key value pair, but the key will be the centroid. What that means is we will do some transformation saying that the key centroid 1, data points 1, 4, 9, 7, all these data points are assigned to cluster 1, and cluster 2, remaining data points 2, 3, 5, these data points are assigned to cluster 2. I get that information into my reducer. This is the most important aspect of MapReduce, wherein I output the mapping function. This is mapping function and this is the reduce function. Yeah, the output of mapper part in MapReduce always is a key value pair. And the critical thing here is that the key is the centroid. So for each centroid, remember, each machine has its own partition, but it has its own centroid. It's the same centroids across. The 2 centroids it has chosen are common across all the machines, all the mappers. Right? So for each, because ultimately what do I need? All I need to care about at the end of this iteration, remember this is one iteration. At the end of this iteration, I need to know the assignment for each centroid. How do I get that? So for this data point, it has its own 100. The centroid 1 gets 1, 4, 7. Centroid 2 gets 2, 3, 5, 6. I get that information over here. I get similar information from the second 100 data points. Maybe 101, 102 are assigned to the first centroid, 103, 104 are assigned to the second centroid. Now, the reduction usually does the aggregation of the results. So now, at the aggregation step, Now I know centroid 1 which came from here had 147, and centroid 1 which came from here had 101, 102. This reducer function over here takes care of only centroid 1. The centroid 2 information over here is computing centroid 2. Centroid 2 which came from here and centroid 2 which came from here. How many ever centroids? You can use that many number of reduce functions. Of course, if you have more centroids, each reducer can use more than one reducer function as well. Right. In the reducer function, you are aggregating the key value pairs you obtained from the mapper function, where each key is a centroid and all the data, the value or the data points associated with that centroid. And that's enough for me to aggregate. This is the most important aspect of MapReduce. So if at all you want to get something out of the tutorial, this k-means the platforms and the MapReduce, how the MapReduce really works. Of course, the coding level, we will talk about the coding. If we have time later, we will talk about how to implement in EC2. The codes are kind of, the installation, everything is self-explanatory, so that part I think you can do it. But this is the most important concept that I want you to get. And remember, this is just one iteration. Now this here, the reducers, now all I have is the assignment. For each centroid, what are the points assigned to that centroid? For second centroid, what are the points assigned to that centroid? I take that centroid and I can compute the new centroid because I know the new assignments. Right? All the data points assigned to cluster 1, centroid 1. I compute the centroid, and that's what I will output as a new centroid. And you will see that that's written to the disk. Right? And that's the issue with MapReduce. And you write the new centroids. The data doesn't change, so data is not transferred. Just the new centroid is sent to the next iteration. New centroid is passed to this again. Same thing, the key value there. This is one iteration, and this is what MapReduce of k means has. You see the similarities, but you also see the differences. Right? In terms of key value pairs, mapping what does reduce to and so. Yes.
Something that is a little bit confusing for me is
Yes.
that key and value. The key is supposed to be unique. So how do you do that?
Key is supposed to be
unique, right?
Yeah,
And
yeah.
each key has just one
Oh no,
value. But the
So
value is
key value pair is like you have same key with multiple values also, right?
So one key can have multiple values.
Yes,
Yeah.
yeah, key value. No, key and value, right? But you have keys multiple times.
Yeah, you can have key.
Yeah, you can. Yeah, so the same key you have it with assignment. That's common enough.
So, but within each mapper, this one key has just one value, right?
Yeah.
Okay.
Yeah. Yes.
So in contrast to the previous cases, now every computer, every reducer is a computer, right? And the resources could be different. Some computers have more memory than others. So my question is like, if we could do like a resource-aware reduction. For example, in the previous steps of the k-means, some cluster could be huge. And the memory could be very small. All these
The advantage of Hadoop is that it takes care of that is you. It doesn't show it to the user. It allocates based on the need from the mapper result. It allocates the resource automatically. That's the resource management layer that takes care of the resources even in a dynamic fashion, like reducer.
Can I change that if I want? Can I have the option to actually say?
I'm very positive on that. I haven't done that myself, but I'm very positive it can be. The newer version of Hadoop, it is possible. Yes. Yeah.
So I can see, because basically your number of reducers are reduced to your K, right? For your K. So if you only wanted 6 clusters, but you had 6 trillion data points, can that be like a bottleneck for the system? Is there like a way to,
these are better than CPUs, right? So, I mean, the reducer is like one CPU you can think of, right? So, whatever CPU can handle, that's not the major bottleneck is the fact that it has to keep writing to the disk and reading to the disk. Apart from that, whatever capacity of the system, you can, I mean, it dynamically allocates how many mappers it needs and reducers it needs. So, it dynamically it does many things.
So a reducer, it's a K. If there's 3 clusters, you have 3 reducers.
Yes.
And if one of those reducers is huge, the system will take care of
yes.
sharing that into several.
Yeah, I mean, why we said only one machine? I mean, we you can have multiple machines on
One
the
producer could be
Yeah,
distributed. Okay.
machines. That really depends on the application and many other. Okay. So actually K-means is more difficult than K-NN is much easier. I mean K-NN you don't have iteration first of all, right? You just K-NN the algorithm is so. Any other questions? K-means everybody comfortable? Because I really want to get the algorithms and okay. So K-NN basically it's you are trying to nearest neighbor is a very important problem everywhere you need, and of course in the data mining community it's more used in the classification setting, which means if you 3 of your neighbors are testing positive, then you will be positive, right? So that's the kind of analysis. If you walk like a duck, talk like a duck, you are probably a duck, right? That's the philosophy of nearest neighbor approach, right? So if you have your query point that are close and it, so you have two things: training data and test data, right? You have the training data to train your model, and you have test data. In some of the literature, you will also see that this is the reference points. All the points in the training data are called reference points, and the testing point is called the query point. You are trying to find for a query point what is the label that I want to assign, and that is the nearest neighbor algorithm. You can see that this is very similar to the centroid distances computation. So I'm not going to do this in much detail. That you have the data, you have 1 million points, you want to find the nearest neighbors, right? You want to find what are the, so you will do the partitioning, you try to find the distances and so on, right? So the GPU code, it will be very similar. Send R and Q to GPU. The Q is the query set, R is the reference set, and Q is the shared memory. This is one of the limitations, the shared memory capacity. So we will talk about the shared memory actually over here, right? So compute the m by n, where m are the query points and n are the reference points. Each processor computes the distance of one query point with the reference point. So basically the query points are broken down into the multiple processor, and the reference points are in the shared memory. We are trying to compute the distance from each point, each of the queries. So query points, let's say it's 2000, right? I have 10 processors. I have each processor has 1,100 query points to compute the distance. Right. Now each point distance to all other reference points is what the GPU processor will do. Right? And then the m by n matrix is basically for each point you sort out all the reference points and you create that as a matrix, right? M rows, m query points, n columns, n reference points, the closest it will be in the first. That's the index of the closest units. Is sorted parallelly using insertion sort, and the indices for each column is also sorted. Basically, the parallelization of K-NN algorithm, once you understand K-means, is very, very simple compared to in K-NN compared to the K-means algorithm. So the m by n, now it's sent back to the CPU, and the CPU will compute the K nearest neighbor. So remember, each point will have the index values of the closest neighbors sorted in a sorted manner, and then you pick the K nearest neighbors in the CPU. So it's just a very simple. No iteration, no sending back and forth like K-means, because it's not an iterative algorithm. It's just done once, right? So there is nothing really new compared to the K-means algorithm that we saw. I think we really running out of time. Okay, so let me quickly go through the multi-core is once again similar. That paired distance matrix m by n. There's nothing much. I mean, you get the point from the K-NN, as I said, is much simpler to the. So the map reduce part, Q and R into the memory, and then each map task computes the distance of each point in query to the reference points. And then basically the data point of query points, if you have 1,000 query points, you can distribute it to multiple mappers. So that is the only parallelization that K-NN allows you to have. And now you can find that there's no iteration again. So it's just basically the output key value there is the key is the data point, and the value is vector of distances from each point to every other point. And then you can do the sorting either in the reducer or you can do that in the mapper itself, right? Because once you have the values, either you can pass to the reducer it can be totally independent of what the mapper does, right? So it's nothing much over here. Sort the vector values and find the k elements in the smaller system. So the reducer output here output is no iterative, and then map reduces square. So now the last few minutes we have Amazon Web Services. So this is where the tutorial. I mean, Amazon EC2 is a very popular cloud computing environment. Very good for academic people, especially in the universities. People do get access, and the email that Kavya has sent, we have $100 worth of computing, and you can read in the code and you can start playing with these platforms, and the instructions of how to get the account set up, everything should be available on the website. So if you have any questions, feel free to email me so that you know how to run on these platforms. I have 2 students working on this, and they will be very prompt at responding as well. So if you have any questions, do email us. Right? So some of the Amazon EC2 advantages, basically you pay for the amount that you need. Okay, if you are careful, you are trying to use only limited amount of resources. You just pay for the amount. So the amount deducted is not just you have like a HPC or something where you have dedicated amount. Whatever effort you, whatever amount of things you need from the platform. I have the list of things also. I'm just going to quickly go through that. And this is a very versatile thing for data mining algorithms, especially data analytics algorithms. And you have complete control over the computing resources and so on. Different applications. And so benefits being the elastic web scale, you can change as you go depending on. Yeah, and you have the access to the root. I mean, it's very highly reliable. It's very secure, and so we have points. I don't think those things. Because I mean, these are taken from the Amazon EC2 website, and on-demand instances, this is like you pay only for the things that you go. It's highly secure, easy to start. It's very easy to configure compared to some other platforms that we worked in the past. And another thing is, depending on your application, it's not just one unit or one instance you try to create. Some of them are memory optimized, some of them are GPU based, real-time or computer optimized or storage optimized. So depending on the application, you can also choose the instances, the different kinds of instances that are optimized for different kinds of things, characteristics that we talked about. So that's important, and it has its own price ranges on an hourly basis. So the one that we chose, so some of the best practices, like you need to choose the correct instance type and correct usage, and definitely close, otherwise close the instance. Once you are done with the instance, close the instance, otherwise it's going to keep charging your account. Some of you might have seen that already, that unless you terminate the entire process, it's going to be automatically charging your account, and you will lose the amount in that time. So that is so some of the configurations that we chose, and remember we tried to keep them as close as possible in the past, because one of our goals was to see k-means, k-min. If you vary the size, if you vary the data size, if you vary the clusters, how much time is it taking in each platform? For that, what we decided is to have the same cost associated with each of the platforms. So each platform is not same cost. So if you have Hadoop with 3 machines, it's not same as having with 6 machines. But to make a fair comparison, if I have to compare Hadoop and Spark, what is the cost I'm putting on Spark and Hadoop? I can make them to be the same. And the number of nodes I get for that cost in Hadoop is what I will use in the experiments, so that I have a fair comparison across 4 platforms. And that's one other work that's going on based on the course. We try to make it as similar as possible to see what is good and what is not. For k-means, on what kind of data sets, where the large data, high dimensional data, sparse data, which platforms are doing well and why they are doing well, right? So those are things that one can really analyze, and of course one can go beyond k-means and k-min. But remember, the GPU code, it becomes very tricky, because if a student has to implement GPU code for a new algorithm, it's going to take forever. I mean, 6 months, 1 year, or something at that range. So you should be very careful about the GPU comparisons. That's why we had to just get the GPU code k-min and k-means available online. To make it work itself, my student had to spend like 3-4 months, even the code was available, to run it on Amazon EC2 cluster. So this work that you're seeing is purely from my student who has spent almost 1 year on different platforms and trying to run all these things on Amazon EC2. Finally, we got everything to work. And as I said, if you have any issues in running, please do email. Okay. So that is the Hadoop instances, and so the configurations, the number of cores, the memory taken. Each, remember, adding more memory is going to cost more in the Amazon EC2. And then the Spark instance, and now the lab. I mean, so let me just finish this, and then I will see if I can run the code and so on. So big data is not about handling, and the different platforms. It's important that you have knowledge on different platforms, and algorithms for big data analytics are still, there are a lot more algorithms that one can think of, and it's very good time that you get into big data because there are a lot of opportunities. There's a IEEE conference, many IEEE journals are starting on big data, so that's an area that you really can make a good contribution. There are a lot of open problems in that area. Next year, January 1st onwards, there's a new IEEE transactions on big data. Already this year, there are like 3 new journals on big data, 4 computing journals. The fact that the new journals are coming, NSF is investing millions of dollars in big data research. Right? So this is an exciting area and exciting time to be in this area. And that's one of the motivations for me to train the new generation to get into big data platforms, big data analytics and so on. So feel free to email me any questions and anything. And if you have the time, if you're interested, I can show online how the GPU is running, or I have the codes running, we have all the platforms running. And but copying the code, everything is going to take a lot of time. So I already have everything on it. I can just run it to show what it is, how it does. Any questions before I move to the yes?
Do you have any kind of benchmark on how fast the K-mean and K-NN on
Yeah, we are still submitting that. I mean, we are still running that. And see, the issue with that is it's not as simple as we think, because if we take a GPU code online, right, and we develop all other codes, we have to make sure that our codes are using the same data structure, because K-means distance computation, one can do in many ways, right? Even, for example, simple sorting. Whatever sorting is done in that is only the same kind of sorting we should do. So the code has to resemble as much close to possible as on all the platforms. Right? So it's not that we can just compare to get the best, because some of them might not have optimized for KNN GPU algorithm. Right? So if you have to compare, we need to make sure that the code resembles as close as possible to the this one. So we are working on it. That's one of the next steps that we are doing. We have the graphs as the data increases, as the number of clusters increases, as the dimensionality of the data increases or the size of the data increases. How the KNN, what is the time taken for the performance? See, we are not measuring fault tolerance, or these things are platform dependent, right? But what is data dependent or algorithm dependent? As the number of iterations increase in K-means, what happens to the performance, right? So those are the things that we have control over. Right? So some of the things. So we are doing those. And of course, we are sticking to K-means and KNN because they are very readily parallelizable. There are other algorithms we did publish before in TKD 2012 on the boosting algorithm. No, but not many people have parallelized the boosting algorithms. We did parallelize the boosting algorithm and try to use MapReduce for a parallel version of boosting algorithm. So it's not just K-means and KNN. There are plenty of algorithms out there which can be applied, which can be parallelized in, especially ensemble methods are very easy to parallelize in the MapReduce or parallel environments.
I guess you also have to deal with programming languages. I mean, MPI and CUDA are very different, and MapReduce is usually in Java.
Yeah. Programming languages, yes. But I mean, Java is, most of the kids know Java, right? But I mean, the MPI or the GPU, oh my God, CUDA framework is very intense. I mean, unless you plan to invest significant amount of time, don't even go to CUDA. I mean, it's like, you're not regarding that, right? Yeah, so it's very intense. But I mean, remember, I mean, the more difficulty you have, the more opportunities you get also, right? So it might be worth it to try it out. So we never know. Yes.
So what kind of strategy does Google use, for example, with that amount of data they have?
They don't reveal like this. I mean, the Google, Microsoft released, so there are these machine learning algorithms. What I explained are the basic ones, right? If you are really interested in machine learning algorithms, there are very good platforms, especially Mahout. Mahout is a very popular machine learning set of algorithms. If you type Apache Mahout, you will get all the advanced algorithms, collaborative filtering algorithms, all the advanced machine learning algorithms, regression trees, everything, how to do it in MapReduce, for example, or how to parallelize things. They have the inbuilt codes as well.
My assumption was that GPU is very energy consuming technique, and that's what Google tries not to use GPU programming.
Oh, no. GPU is more real time. In fact, Google or some other companies using GPUs now for deep learning and trying to do more compute intensive tasks using GPUs. GPUs are gaining more popularity compared to any other platform. GPUs are gaining more popularity now, and because the code has become much easier than what it used to be, and people want to, especially the entire Bay Area is looking for real time solutions, and that's why Spark is getting more popular than Hadoop. Hadoop actually is the old generation. Now it's almost getting saturated. In 2 years, I won't be surprised if it almost dies out, because people have developed, because real time is a very important thing. People used to think, okay, scalability, fault tolerance are the two best things for Hadoop, right? I mean, you can see from the comparison. But they realize that real time is more important than scalability. I mean, scalability power you can increase by, but if you can't get real time, then it becomes, everybody is going for real time. That's why GPU is getting more popular. You have.
So the one difference is that because writing it at disk and writing it to the memory, there's only one difference between Hadoop and Spark, or much more.
See, because of that, that's not a simple difference, right? Because of that, every layer in the system, it doesn't use HDFS anymore, right? It has its own distributed file system, because writing to memory, it has its own way of writing things, and so the entire architecture is completely different in Spark. But the main, from the user's perspective, when we see, everything remains the same except for the memory part, for the characteristics that we are thinking. But the original architecture, obviously, it's a total revamp of what we had from Hadoop, right?
Yeah. So is Spark still batch processing? Is it just like Hadoop, like you just made the job, you send it out to the cluster and retrieve? So is Spark still batch, but it's a lot faster?
Yes, a lot faster.
But it's still batch.
But it's not comparable to GPU in real time. It's faster, but it's not as good as GPU in real time, right? But it can handle. It has all positives of Hadoop, right?
So in the interest of time, maybe we'll take a quick break, and then any of those that have questions in terms of running this in EC2, Dr. Reddy will be here. There's also 2 or 3 of you who have volunteered to help. So let's take a quick 10-minute break. We'll let Michael set up as well, and then if you guys have any questions for Dr. Reddy, we'll be around to help, and then some of our volunteers as well. Yeah, give him a hand.